Hey guys, welcome back to quantum mechanics. So we've been talking about time-dependent perturbation theory. Our first lecture, we focused on kind of a standard approach to computing transition amplitudes, which are the main, or transition probabilities, which are the main things that you try to look at when you're doing time-dependent perturbation theory. And last time, what I did was to muck it up by introducing some new formalism. And hopefully you weren't totally confused. I mean, it's natural to be, confused a little bit when you first encounter this formalism for working in time-dependent perturbation theory. But hopefully, as time goes on, you'll get more comfortable with it, and you'll see that it's really like I tried to stress several times last lecture is just another picture, another time, the way that we work with time evolution and time dependence. So what we did was we went back to the beginning and we said, okay, well, we remember when we were working in time evolution, we basically had two pictures that we were able to work in. One were the state cats evolve with time and operators are constant. That's a Schrodinger picture, and the other picture was the Heisenberg picture, where the vice versa is the true. So state cats are constant in time, but operators and the base cats evolve with time. And we always said that whatever picture you work in, the physics better be the same, right? And so, and then the way we quantify that is saying that, probabilities that we compute in these pictures have to be the same. So how do we want to use this to our advantage for this time-dependent perturbation theory stuff? Well, we basically defined a new picture, right? So when we're working in time-dependent perturbation theory, we have basically two sources of time evolution or time dependence. One coming from just the normal evolution of time, so the piece coming from the unperturbed Hamiltonian. But now in our situations that we're considering now, we have time dependence coming in with the perturbation Hamiltonian. And so since we've known since last semester that first piece of time dependence can't cause any transitions between states, we'd like to just get rid of it, right? Or just kind of push it under the rug because it's not going to affect, our calculation of transition rates. So we wanted to define a new picture where we basically rotate. So if you have this picture in your mind of time evolution as our state vector kind of rotating in our vector space, we wanted to transform to a frame where we're basically sitting on the vector, and so the only time evolution that we can observe is coming from the perturbation Hamiltonian, right? And so this is what we call the interaction picture, which will become, like I said, it'll become clearer once we get to scattering theory, which we're going to start today. So we worked through the formalism, right? And then a lot of this stuff is basically review. We went through it last semester when we talked about time evolution for the Schrodinger picture, and then the Heisenberg picture. So a lot of the stuff we did was the same type of operations and things, right? So we began by in particular, in this interaction picture, we defined a new state, right, which we can build out of the Schrodinger states. So these are the states that evolve with time, right? And in our case now, this is going to have time dependence coming from the unperturbed Hamiltonian and the time-dependent perturbation Hamiltonian. And so what we do is we define this interaction ket to be the Schrodinger ket, but we want to subtract off that piece that's coming from, or subtract off that time-dependent part that's coming from the unperturbed Hamiltonian. And to do that, we can multiply this state by the Hermitian conjugate of our Schrodinger time evolution operator. Okay, and like I said, this is kind of equivalent to, we're moving into that rotating frame where the time, we can't observe the time dependence coming from the unperturbed Hamiltonian. And so like I said, we worked through the mechanics of it. We found this thing satisfies a Schrodinger-like equation, right? But we've subtracted off the unperturbed piece, so the only piece that really matters as far as the time evolution or time dependence of this new state is concerned is this interaction or the perturbation Hamiltonian, right? And that's exactly what we wanted to begin with. So what else did we do? So let's see. So I talked about the fact that you're working in these different pictures, but the physics has to be the same. So it's the same stuff that we talked about before. We defined operators in the interaction picture like this, so they're related to their Schrodinger picture counterparts being sandwiched between the Schrodinger time evolution operator. And we were able to construct the eigenvalue equation. And then we looked at how these operators evolve with time, right? And what we found was basically a Heisenberg-like equation, right? So the time evolution of our interaction picture operators depends on its commutator with the interaction Hamiltonian, right? Our interaction picture Hamiltonian. Okay. And let's see if we did what else did we do? Anything interesting? Then we worked through, so we wanted to construct the time evolution operator in the interaction picture. And what we found was basically that we have to do this in a perturbative way, right? So at 0th order, we would expect this thing to be just the identity operator. And at 1st order, it's just going to have one piece of the interaction Hamiltonian in it, right? But the way we do this is we kind of it's a recursive way of building up the time evolution operator. And so basically, we start with that general equation, right here, right, which is we called it a solution, but we noted that UI appears on both sides, so it's really not a solution. But we can, kind of recursively or perturbatively solve for this thing. So we recursively plug this expression for UI in for itself, right? And then that way we build up kind of a perturbative expansion, right? So up to 1st order, we had identity operator. And then, so the UI0 comes in here. So this would be the 1st order term. And UI0 is just the identity operator. So the 1st order time evolution operator would look like this, right? And then we went through and we wanted to make sure that we were able to reproduce the scattering coefficient or the transition coefficient. Sorry, I'm getting ahead of myself. The the interaction or transition coefficient that we computed previously using the more standard approach. And we were able to show that, sure enough, we got the same thing back out. And then the last thing I did was it pointed out that if you keep expanding this thing, you'll see that it's basically, like I said, a perturbative expansion and the interaction picture Hamiltonian. And if you remembered from last semester, this thing is called the Dyson series. Okay, and it's the way that you compute the time evolution operator. Okay, so the idea is, basically what we did last semester is that, instead of trying to solve for the time dependence of our states, of our our final states, we construct the initial state. We know what the initial state is, and then we solve a Schrodinger-like equation for our time evolution operator. And that thing will only depend on, in this interaction picture, only depends on the interaction Hamiltonian, the perturbative piece. And from there, we can just once we have that solution, we can apply that to the initial state to obtain the final state. Okay, so that's where we ended last time. And what I want to do now is just go ahead and move into scattering theory and see how we can put this to use. Okay, so you'll probably have some homework problems on scattering theory that it won't have. I don't think there are any interaction picture problems, but there are. So there are some standard problems in computing transition rates and transition probabilities and things like that. But I think they're all problems that are, undergrad quantum level. Okay, but I just wanted you guys to have some problems or have some homework on time-dependent perturbation theory. Okay, so what we're going to do now is put this to use, this stuff that we've been talking about, and put it to use in scattering theory. Okay, so scattering theory is one of those topics where I have to start off by saying that the importance of scattering theory can't be understated. Scattering experiments are basically responsible for everything that we know about fundamental particles. Okay, and so these are situations where, if you remember back from your modern physics class, or maybe your undergrad quantum class, you talked about all those old experiments where I can't think of the guy, Rutherford and people like that. They did all these scattering experiments, and that gave us an idea about the structure of atoms, and then the structure of nuclei, and then nowadays we even understand the structure of nucleons, so like protons and neutrons, right? But like I said, everything that we know about the structure of atoms, nuclei, and protons and neutrons comes from scattering experiments. And like I just said, everything that we know about fundamental particles. So fundamental particles are particles that, can't be broken down into smaller pieces, right? So those are like electrons, quarks, photons, gluons, things like this. So particles that are truly fundamental. In other words, they don't have any internal structure, like a proton or a neutron or a nucleus. But these are, one of the things you learn in your modern physics course is that the higher energy means you can probe smaller scales, right? And so to probe fundamental particles, we have to go to extremely high energies. And so, this is like the case now at the Large Hadron Collider, right? These are very, very high energy collisions, and that's how we learn about extremely small scales. So in general, when we do scattering experiments, these experiments are giving us, or can give us, information about not only the target that we're scattering off of, but we could learn something about the projectile, so the particle that we shoot at the target, and the force or forces between the two, right? Between the projectile and the target. So typically the way scattering experiments work is that two of these are known, right? So we might know, we might know all the properties of the projectile, and we might think we might know what the target is made up of, and what we're testing for is the forces between them, right? And from the results of the scattering experiment, we can extract that information. So kind of the prototypical case, but it's kind of outdated now, is what the Stanford Linear Accelerator Centers, or SLAC. Nowadays, it's more of a condensed matter lab, I think, than a high energy or nuclear lab. But SLAC was a place that was an important place where a lot of important discoveries were made in high energy physics and nuclear physics. One of those results were experiments that were carried out where high energy photons were used to bombard neutrons, right? And neutrons are, as you might guess from the name, they're neutral. They're electrically neutral, right? And photons only interact with charged particles. So you would expect that, if you shot photons at neutrons, you shouldn't see any type of interaction or any type of if neutrons were truly fundamental, they shouldn't interact with each other, and they would just go zooming right by each other, and nothing interesting would happen, right? And we know that at the time that these types of experiments were being done, we knew that photons were basically point particles, so they were fundamental. And what was being tested was the structure of a neutron. Is the neutron truly fundamental, or does it have some internal structure? What the photons were able to show is that the neutrons are actually built out of charged constituent particles, right? And they're constituent particles, they're charged. So what happened was the photons would come in, and you would see some type of interaction. So you would see some deflection of the photons, and that told us that the neutrons were made up of constituent particles that had charge. It's just that the total charge of those constituent particles had to add up to zero, right? Because we knew that neutrons were electrically neutral. And from by measuring the angle of the deflection and different and other types of observables, we were able to learn that these constituent particles are spin 1/2, so they're like a lot like the electrons. But the weird thing was that they had fractional charges, right? So instead of plus or minus E, they had charges of 2/3 E or minus 1/3 E, right? And it turns out that these constituent particles are now known as quarks. And there's actually 6 of these guys. So there's let me see if I can remember, up, down, charm, strange, bottom, and top. So there's 6 flavors of these guys, and they get heavier as you go. So up and down are the quarks that are mainly responsible for normal matter. So they make up the protons and neutrons. And then there were strange quarks, and then charm quarks, and bottom quarks, and top quarks, and they get heavier as you go up. Okay, so that's just one example of the importance of scattering experiments. But there are dozens of examples out there of how scattering has kind of advanced our knowledge of fundamental physics. Okay, so before we get into the real meat of scattering theory, I thought I would just remind you really quickly about scattering in one dimension. Okay, so this is the type of scattering that you consider when you're doing undergrad physics. Maybe some of you had 3-dimensional scattering, but for the majority of you, I'm sure you probably only just had scattering in one dimension. Okay, and so what we're going to be doing is real world scattering. So we're going to be working in 3 dimensions. But let's just start by reviewing real quick one-dimensional scattering. So the question that we're asking is, in these situations, is if a beam of nearly monoenergetic particles, so remember we're dealing with particles that we can't really define a precise momentum, but we can define an expectation value of the momentum, and so there'll be some spread. It'll be like a wave packet, right? And these particles are incident from the far left, so they're coming in from what's basically x equal minus infinity, and they come in and they scatter off of some potential, right? And this potential is finite in x. In other words, it has some small spread, and what happens is it basically tends to 0 as you go out to x equals infinity, right? And so the main question is, when you have these types of scattering, so you have a particle come in and interact with some potential, what fraction will get transmitted and what fraction will get reflected, right? And these are denoted by these T and R coefficients, right? So the basic setup looks like this. Okay, so I have my particles coming in from the left, right? And here's my potential. It's just some step potential, right? Some finite potential. And let's say we have, so we're shooting our particles in from the left, and we have a detector over here on the far right, and we have a detector over here on the far left. Okay, remember, we're just working in one dimension. All right. And what we're asking is what percentage of these particles get transmitted and which percentage of them get reflected. Okay. So this problem can be solved, if you recall, by writing down the wave functions in the three regions, right? So in regions 1 and 3, we have basically free particles, right? There's no potential that they're interacting with, so they're basically free particles. And then in here, it depends on the height of this potential on what the form of the wave functions are inside of this thing, right? Or in this region, I should say. Right. So for example, in this case, where we have particles coming in from the left, we can write down the wave function in region 1, which is this region before we get to the potential, right? And so we would have a wave function that looks like this. So we have part of the wave function that's coming in from the left. So that would represent the incident particles, right? So the incident particles coming in from the left. And we would also have a piece of the wave function that's coming from the reflected part, right? So the wave function in this region is going to be a linear combination of the incident and the reflected pieces, right? And you know that these guys are traveling to the right because of the sign on this in the exponential, right? And likewise in region 3, you would naively, write down again the same type of form, where here we have the transmitted part of the wave function. So this is the particles that are traveling to the right. And in general, we would write down also a left moving component, right? But physically, we don't expect that there to be any left moving particles in this region, right? So what we can do is we can set this coefficient D to 0, right? Just on physical grounds. And so what we would do is use the remaining coefficients, right? So we basically write down the wave function in regions 1, 2, and 3, and then use our boundary conditions, right? And do the matching between regions 1, 2, and 3. I haven't written down the wave function in region 2, but it doesn't matter for this discussion, okay? So we would use matching on the wave functions and their derivatives at the boundaries, okay? Just the normal regular boundary conditions when you do these types of matchings. And so what you find is that you can compute basically the reflection coefficient, so the probability that particles are reflected, and it just goes like this coefficient B over A squared, modulus squared. And the transmission coefficient is just basically the amplitude of the transmitted part over the amplitude of the incident part, and that's modulus squared. Okay, and so this is typically what, the types of things that you do when you study scattering in undergrad. All right, so what we want to do is start to talk about scattering in 3 dimensions. Right, so there's a lot of similarities, right, but there's also several complications because now we're dealing with additional dimensions. So the first kind of complication is that now our beam is not just one-dimensional moving to the right. It has some finite dimensions in the transverse direction, right? So we would have some beam of particles where imagine each of these little arrows inside of this thing are actual particles, right? And so we have a kind of a pulse of a beam, pulse of particles coming down, our pipe that we're going to use to shoot the particles at the target, right? So our dimensions here are not only in this direction to the right, but we have some dimensions, in the transverse, right? And we usually parameterize this dimension in the transverse direction by what's called the impact parameter, okay? And it's just the coordinate in the plane perpendicular to the direction of travel, right? So K is basically our momentum vector, right? Our wave vector, and it's in the direction of the direction that these particles are traveling, and the rho, or the impact parameter, is in the transverse direction, so it's in the transverse plane. Typically, in real world experiments, the distribution of particles in this impact parameter plane is not uniform, right? So as you go, it's typically more dense the closer you get to the axis here, right? And it becomes less dense as you move outwards, right? And so that affects the results of scattering experiments. And a lot of times you have to account for that, especially in real world experiments, right? And so, what was I going to say? So this thing is only, so there's some cutoff where this thing is basically uniform out to, right? And it's, that's when the pencil, the distance, okay. I'm not sure what I'm trying to say here, but so basically, the only part you have to consider when you have this type of, I think I have a picture down here actually. Yeah. So here you would see this would be like the impact parameter, right? But here's our scattering potential, and so we only have to consider rho out to the range of the potential, right? So all the stuff that's beyond that doesn't really contribute to the results of our experiment. Okay, so let me go back here. So for example, we might have something that looks like a Yukawa potential, right, with some finite range. And we'll talk more about that later, okay? So the main question that we try to answer in three-dimensional scattering is what's the rate at which particles get scattered into a faraway detector that subtends a solid angle, d omega, in the direction theta phi, measured relative to the original beam direction. That's a big mouthful. Okay, so let's go back to this picture. So basically what we're trying to do is we're trying to compute the probability, or the rate at which particles that get shot down this beam pipe in this form of this beam will scatter off of this potential and hit this detector, which is at some direction, which is measured in spherical coordinates by theta and phi, the azimuthal angle that's not shown here, right? And this detector is going to have some small finite range, I guess you would call it, right? And that guy, that range, for lack of a better word, is just described by the solid angle d omega. Okay, so we're looking at, we want to know the rate or the probability that particles get scattered into this faraway detector that subtends this angle d omega. All right, so that's the main type of question that we're trying to answer. So let me just say this in words. So typically what we want to do is calculate what's called the differential cross section, and we'll talk about how to basically how to derive this expression. But in words, it's just the number of particles scattered into this small angle per second divided by the number of incident particles per second per area in the rho plane. Okay, so it's just basic. It's a lot like those transmission or reflection coefficients. Okay, and so let me just outline real quick how we're going to do this, and then we'll stop and we'll pick it up next time on how we'll get a little more mathy with it. Okay. So our main goal is to compute this cross section, okay, which is related to the probability or the rate at which particles get scattered into this detector. So what we'll do is we'll take some initial wave packet, right, and it'll have some mean momentum and some mean impact parameter. We'll expand this wave packet in terms of the eigenfunctions of our Hamiltonian, right? And this wave function is going to have two pieces. So this is going to sound a lot like what we did in one-dimensional scattering, right? So we'll have some piece of the wave function that's coming from the incident particles, right? And then we'll have some piece of the wave function that's coming from the scattered wave. Okay, so this is a lot like the situation back here when we were doing one-dimensional scattering. It's a lot like we're in region 1, right, where the wave function is made up of the incident and the reflected pieces. Okay, okay. And we'll only take, when we do this, we'll only take solutions for the scattering experiment, which are outgoing. Okay, so that's like the pieces that are actually scattered from the, if you think about it in terms of this picture, the scatter wave function is going to be moving outwards, right? It's going to be propagating away from the sky. So it's a lot like in region 3 of the one-dimensional scattering, where we set that D coefficient to 0 because on physical grounds we wouldn't expect particles to be moving towards the potential. So once we have those solutions, we'll propagate the wave packets by including the normal time evolution. And then what we'll do is identify the scattered wave as t goes to infinity. So this is going back to that picture that we've talked about several times now, where the scattering potential is so small compared to, the dimensions of our experiment, that we can set the initial time to minus infinity, the final time to plus infinity, and likewise for the dimensions, we can set, we can treat those as being out, or being out at plus or minus infinity. Where was I? Okay. So we'll be able to compute this probability density, and from this guy, we'll be able to compute the number of particles per second in the rho plane that get scattered. And then we'll find that that all this could be done by considering what's called a static solution and working in this limit where r goes out to infinity. So this is what I was just saying. Okay. And so what we'll do is I'll stop there. Okay. And I know that outline probably makes no sense at all. That's okay. As we get into it, we'll come back to this and hopefully try to make sense of it. Okay. All right. So I will see you next time, and hope everybody's well, and take care.